Terrel from the University of Texas. It's all yours, Andy.
Thanks a lot. So we wanted to take a moment to recognize a lot of the different Pythons that are being built just for speed. SciPy community has often been very concerned about speed, and we've done some really interesting tricks to get speed. But what I'm going to do here is we have a panel of people who are all trying new methods of getting speed and trying to speed up not necessarily just the SciPy stack, but actually more of a general Python community. Our first panelist is Travis Oliphant of Continuum Analytics, well known for creating NumPy and being an advocate for Python in many places throughout the world. Our second panelist here is Jeff Bezanson. He works on Julia, the new Julia language, and he's kind of coming from an insight outside the Python world, but very much of we have a general programming language that can have a very Python, very nice syntax level. And our last panelist is Kurt Smith. And Kurt, he wrote FRAP, but he wants to be known as a Python guy who used Fortran to make things fast. But Python, for those who don't know, is a kind of a variant of the Python language where you add a few annotations and it can generate C or Fortran and be very fast in that sense. And so these are our panelists. The format to the discussion is going to be me ranting a little bit about different performance metrics, benchmarks, things that we've seen in the past. These are common things that we see in the internet, or most of the things I try to make sure that we had benchmarks that are well known among Python users. The second kind of thing we're going to do is each panelist is going to give a kind of a 5-minute call to arms for their method, why their method is working and how it works, and maybe not too much about how it works, but the real reason why they're pursuing this method. And then the third point is up to you guys. I know there's a lot of questions out there. I see a lot of people asking, how are we going to get performance out of Python? Is performance what we want? And so this is your time to ask not only the panelists who are definitely experts in this subject, but also if anybody else has some comments or things to say. It's really trying to make this a discussion-based approach. And finally, we have I help with the Insight podcast every once in a while. The most fun part of the Insight podcast is a 1-minute rant at the end. And so we'll give every panelist a 1-minute rant of anything they thought about or anything like that. So no worries, it's all being videotaped, and we'll show your mothers later on. So the first question I would bring is to frame the performance debate is CPython fast enough? And if you watch Guido's PyCon video from the last PyCon, it's one of the trolls. It's like, oh, Python's not fast enough. And Guido always says, it's fast enough for me. I think that a lot of people in this community probably will say, yeah, it's fast enough for some things, but it's probably not fast enough for all things. And that's why we've dived down into dual language and lots of other things. But there's a lot of other people on the side, such as PyPy, which comes and says, oh, no, we're faster. We're much faster than you. Just believe us, and the magic compiler. Don't look inside of us. And for those who haven't seen David Beasley's introduction to PyPy, I highly recommend going online and looking at what David Beasley has to say. And I think that's critical. But it's critical we learn from PyPy, and how do we incorporate that in our own side. SciPy, we know very well. Python, we can be as fast as C. JIT, there's a whole lot of JITting out there these days. Some people, I don't know if everybody even knows what a JIT is sometimes, and they're using JIT in many different ways. But at the end of the day, they're all trying to say, we don't have to write C, we can just JIT, right? We can just take something else. And Julia says, we don't have to write in C, and we don't have to look inside, but we're clean. We're clean like Python, and I guess they do use JITting, but they don't have to write in C, and they're fast as many cases. So on the PyCon email list, there was an email from Victor Steiner, and he wanted to create a new CPython that was faster. And he had this full list, and this is in response to Guido's Python's fast enough for me. Well, it's obviously not fast enough for a lot of people. So there's a large list of people who've tried to speed up Python, including the Google-backed unladen swallow that has a nice kind of aftermath of what they tried to do and why it didn't work. And so there is a lot of people out there trying to speed up Python, and they're fundamentally trying to do quite different things. And so I won't dive into this list too much, but I will say let's just look at 2 benchmarks that are common among scientific type computations. And if people were at Brian Catanzaro's, sorry Brian, if you were at his talk this morning, he gave these benchmarks as well for a GPU. But the Laplacian kernel, Prabhu wrote Performance Python, I think back in 2008 on the Laplacian kernel is very typical of PDE solvers. It's a bandwidth limited code, meaning that we have a lot of words coming in to the compute with and not very many coming out. Not very many computations to be done. And then we have the Mandelbrot set, which is getting kind of I don't know, too much emphasis sometimes, but it's one of the cases where we're really compute limited. We can't compute the numbers fast enough. So we can get, since there's pretty much no data coming in and there's only one number coming out per grid point, we can actually do a lot of computations. But it's typical of a simple map. If you're into the map-reduce world, you have the map, but the reduces, everyone knows, is the hard part. So if we can't do the map part right, then we're kind of hosed to begin with. So the performance Python benchmarks that Prabhu put up, he gave this talk where you have Python, Psycho, NumPy, Blitz, inline, doing some inline, okay, I've forgotten what the inline and fast inline is, but Python, Fortran, you can kind of see how you can look at all the different types of places where, so Psycho's an optimizer around loops. NumPy we know very well, but even with NumPy expressions, you're not super fast. If you go to Fortran, that's where you get a lot of speed, but if you do some really fancy C++ stuff with Blitz, then that's kind of the limit of what you're going to. And then you can see if you have a pure C++, that's kind of what people shoot for a lot of times. It's like, can I be as fast as pure C++? Now the Mandelbrot, there's this kind of nice benchmark on the internet, and there's a link there whenever people get slides. But they go through the Mandelbrot set, and they have very simple kind of Mandelbrot computation. And what I'd kind of like to show here is, so you can jump from Python to Cython very quickly by just decorating a few input variables and temporary variables. And so that actually goes as fast as their C version, which was a fairly simple C version. But also PyPy gets pretty darn close. And all PyPy does is run the same code that Python does. And what is PyPy doing to make it so fast? But coming from a scientific computing tool background, HPC tools are far and away, all the way at the other end. Now, this is a little bit unfair because getting HPC tools to work requires a lot of work. So maybe you spend so much time getting the HPC tool to work that you don't actually really see the real gain. But just to give an example, Andre, which was mentioned earlier today, has this great NumPy post about, hey, just doing base Fortran is 16x faster. He has kind of a nice little branch on GitHub about doing NumPy with Fortran. It's quite interesting. And then for an APUG demonstration, I showed that you could just use 5 lines of OpenCL inside Python, and you could actually get about 500 times faster on your CPU. If I went to a GPU, it would give me another factor of 10. So there are all these tools that are being swirling around, but kind of the hotness today is I would characterize as legit compiling, just-in-time compiling, with Travis will kind of give us a 5-minute on. Compiling to lower languages with some information, some type information, or some annotations, which Kurt will give us some idea on. And then domain-specific languages, although Julia is a general-purpose language, it has a very kind of style to it that is specific to it, and by breaking out of maybe kind of the framework we have, what they can do that's faster, and Jeff will give his 5-minute on that. So Travis, if you would.
Okay, who wasn't at my talk this morning? Can raise your hand. Just give a brief overview then. So Numba is basically a Python syntax to the low-level virtual machine, IR, intermediate representation. I believe that is the underlying to the Julia language as well. That's true. So in some sense, it's kind of taking Python syntax and producing low-level virtual machine intermediate representation, and then using that machinery to generate machine code. The idea is to be able to take small snippets of code that we're targeting, certainly first off, is numeric code that you just want to write some Python expression but have it be very, very fast. So it integrates nicely with the entire CPython stack. You can have all the tools you are used to having and just get that one piece of code or that whole module or that whole, potentially even a whole set of shared libraries built quickly and using the same language. So that's the motivation behind that project. And I don't know if I can say more about it. I mean, basically, it's like the speeds you get are the same as if you had written C code, essentially. The hope is to take and go beyond that now and start using some intrinsics, some GPU intrinsics, or some threading libraries, but all of that has to be done separately, just the same as you have to use an OpenCL compiler, or you have to use OpenCL additions to your C language. You'd have to do the same thing to Numba, and you could do the same thing and just insert those calls in the right place in the LLVM. That's the sort of thing we'd like to work now. We have the basic stuff working, we'd like to go beyond it now.
All right, Kurt, if you had some words on why Cython works well for speeding up Python.
So, as you mentioned, Andy, Cython is kind of in between Python and C. I like to think of it as a language. Think of it, first of all, as a language that's whole design is to smooth the gradient between Python and C and lower level languages. So it just makes it easy to inject type information into Python and make that information available to compiler to give you access to C speed. And secondly, I'd like to mention how strange it is to have, this is the only conference where Cython can be the old guard in anything. Cython is the old way of doing something, and here's the new stuff on a panel discussion. So, but yeah, it's. Well, actually, I'd be really curious. How many of you? I'm sure most of you have heard of Cython. Let me see a show of hands. Who has heard of Cython before? Who's using Cython in a project? Okay. Number of you, and of those of you who use it in the project, you probably aren't exposing anything of Cython to the end user, right? Because it's giving you a Python level over compiled code, and it's kind of like an infrastructural layer for tremendous number of Python projects now that want to access either externally compiled codes, or if you just want to take Python code and speed it up for whatever reason. So it's becoming part of the infrastructure of other projects. And do you use Cython at all as part of the layer between, you mentioned LLVM Pi, Travis. Does that use Cython?
No,
for
it doesn't use Cython.
It doesn't, okay.
No. I'm interested in the interoperability between Cython and NumPy, especially speaking the same kind of languages about typing and that sort of thing. Mm-hmm. But no, it doesn't, it's independent currently.
Okay. But there was work done, very nice work done by Dag Selubotn a number of years ago to bring in, basically make NumPy support a first-class citizen within Cython. So Cython understands NumPy arrays very well, and it's very much tailored towards numerical community. So that's why it's very much a big part of this world here. Another big reason why I like Cython is that it gives me full control at whatever level I want to tap into that control. It allows me to pull in a C library that's separate and doesn't know anything about Python, or I can just incrementally improve my Python code and speed it up with more information as I like. And so there's very nice kind of incremental feel to it where I can do as much work as I like, and often each level of work that I do is up to an order of magnitude speed up over the previous level. So that's my preference. That's why I like to use Cython.
All right, and Jeff, the magic behind Julia.
Okay, so to me, actually, performance is not just a number necessarily. The way I think of performance is it's really a curve of program runtime versus human effort. And as you work on it, the runtime goes down. And so what you really want is not to necessarily get the fastest possible runtime, but you want it, in some sense, you want it just to be more likely that you will get a good runtime as soon as possible. So this is a sort of a more nuanced thing, right? Because in some sense, if we say we can run something as fast as C, like on some level you shouldn't be impressed, right? Because C is also as fast as C, right? So what you want is that performance as soon as possible in your development cycle. And so I think about how we can make it more likely that that will happen. And so the way I see this, getting that is to have a compiler that can do a good job of sort of flattening out and eliminating overhead in as many places as possible. Because as a programming language, you don't know what the bottleneck of someone's application could be. Any given thing that your language does could be somebody's bottleneck. So you have to be able to sort of eliminate basically as much overhead as possible. In general, you'll have someone else's, basically somebody else's data producer, and you want to write some data consumer over that, and compose these things together, and you want that to run with very little overhead. So to me, that's sort of the problem. And so to get things like that to work, you want to have these things composing together efficiently. So what really matters is sort of the user interface to the performance. Is sort of the important thing. Is how do you express the code that will let you get to the performance? And so that's why that's why we take the approach that we do, writing these method signatures that let you simultaneously. I mean, it expresses your class's behavior essentially at the same time as giving the compiler useful information. So that's what I think about. I want to be able to compose together different abstractions, and it gives you a lot of development leverage, because you can just separately develop things like you can write an algorithm over just an abstract vector, and then you can write something else that knows how to take vector slices of some kind of data set and run one on the other and get good performance. And that's the kind of thing you want to be able to do. So it's not just to me, it's not just writing a particular kernel and optimizing a kernel. I mean, optimized kernels are great, but to me it's not just that.
Thank you. So while everybody's rushing to the microphones to ask their own questions, I'll start with mine. So feel free to line up I guess there's a microphone here. Is there one over, just over here, okay. So the microphone's over here, guys over there, walk all the way around. And there's, we're one to there. So my first question, you guys, is what are better benchmarks? Laplacian and Mandelbrot are pretty simple. We can't really measure how long it takes somebody to write pieces of code very much. The computer benchmark, computer language benchmark that you find online tries to categorize it in code length, but what do you guys want to see in the benchmarks to evaluate your methods? Any takers? Okay, so Travis, what do you have?
Well, I'd like to see finite difference time domain expression. I think there was one on Maxwell's equation update that I think probably also was looking at. Something that involves a little more kind of array expression slicing, array splicing, and that sort of thing. That'd be a nice benchmark.
Yeah, I guess, I would want to see, good benchmarks are really hard to do, but I would want to see it broken down in terms of the data sizes involved and the nature of the algorithm, if it's a stream kind of algorithm or if it's doing something iterative. And if to interpret the question as what's Julia's favorite benchmark, I think right now probably what makes us look the best is programs that manipulate lots of small arrays, actually, because if you have 2x2 matrices and that sort of thing, because that's the case where even the calling overhead of something like BLAS is going to be significant. So if you're doing lots of small matrices, the way that we tend to specialize calls to specialize in inline things, we get generally really good performance on those kinds of things.
For Cython, really nothing to add other than when I'm looking at benchmarks that have been done, I really like the ones that are coming from users that have in their own problems or real-world problems, and they point out, okay, this is relevant to what I'm doing. So, whether or not you've squeezed every last bit of performance out of this by pulling out all these tick trips or unrolling loops with some sort of generator, something like that, to really, not that we would be doing that in our projects necessarily, but still, there's so many games that can be played with benchmarks that I definitely prefer to get benchmarks from real world code that people have submitted for whatever reason.
Yeah, the only benchmark that would really convince someone is their own application.
Exactly.
I totally agree, yeah.
All right, question.
So along the same lines as benchmarking, there's also like profiling and code instrumentation and so forth. Could you guys comment on either the value of instrumenting your code, or the how easy it is to do within your framework, that sort of thing?
Cython has it's a big part of Cython, our profiling and instrumenting your code. It provides a lot of control over, there's actually a whole ability to turn on and off profiling at whatever level you like, the module level, the function level, inside of functions, things like that. You just put in simple comments that say Cython.profile equals true, I believe. And that enables Python's profiling module to access the Cython compiled code as if it were just part of regular Python. So it folds that Cython compiled code into Python's profiling, and then you can leverage the profiling and timing abilities of IPython just to access the underlying Cython stuff. Also, along with that, like debugging, Cython has its own debugger, basically, that allows you to go between the language barrier between Python and the Cython compiled C stuff, which is really, really nice. I have no idea how that was accomplished, but it's quite impressive feat to be able to cross that language barrier, which has always been a major impediment prior. So,
so for our part, Julia is not very mature yet, so we don't have really good debugger and profiler tool support. But someone actually has started doing kind of a proof of concept profiler for Julia, actually. So there's some stuff there, but yeah, not a mature tool chain, certainly.
And Numba's in the same boat, so we're okay there. I mean, these things are important for developers to really take advantage of something. There are definitely hooks. I mean, nothing in the framework of either Julia or Numba prevents something like that from working. In fact, I'll likely leverage a lot of what Cython's already done. The annotation tool that he talked about, sort of the ability to see what's fast and what's not, even aside from, I mean, just that, not even having to run a profile, but just see what got converted to low level and what remained at the high level is very nice. And then I think memory management tools are nice too, just being able to understand. And we could use a lot more of those in the NumPy community as well. Just being able to see what data, what memory you're using, and how fast the code that you've created is working on those data. So still in process, but nothing. LLVM debugging is an interesting question. I mean, you essentially have to put in debug hooks. I mean, you basically have to do a lot of that. But the LLVM projects, there's an LLVM debug group, I guess an LLVM debugger. So that's where you benefit from being part of a larger compiler culture, for sure. And so I'm going to be very interested in what Julia does there.
So we actually do
the same things.
We do emit LLVM debug metadata.
Yeah.
So we can get pretty good stack traces, for example. We can get source line numbers and that kind of thing.
Yeah.
So thinking in terms of the way that John Hunter contextualized the entire stack of software components in the scientific Python ecosystem of core, and then on top of that, and so on. There's been a lot of changes recently, and a lot of very interesting things going on in the scientific Python ecosystem. Can you suggest ways that we can, as say implementers and users of those things, use new items while still remaining forward compatible? Like sort of a philosophy.
Tough question.
Mm-hmm. Well, one thing I can pitch out there is, so Cython has a number of different backends now, and it has a C-types backend, for example, and so basically take your Cython code and it generates a pure Python module that has the type information included in there, and it's available for use by something that understands C-types, which is relevant for PyPy. And so for a while there, Cython saw PyPy coming along, and we're in the same space of speeding up Python, and we wanted to be able to play with that project and make it work nicely. And I would not, so since we started expanding, and we also generate C++, C, and C-types code, we also generate C# code. So I would not be surprised if, since we have that, we've started to generalize our backends to be able to play with other projects there too. So you can have this common language of whatever, I guess the domain-specific language that Cython is, and then it can be, you don't have to think about what backend it's being generated to. It can play with those things and tap into whatever work other people do in the future. So.
I would say one thing is to, if you are writing a hand-coded C extension, rethink that probably is gonna, that creates the most. Who's Emerzi?
I have no idea.
Just the C API, Python has a nice C API, but it's, it changed when going to Python 3. It doesn't exist in the PyPy world. It doesn't exist across multiple other runtimes of Python. Julia trying to support the C API of Python, I'd actually interested in kind of the other way of actually Python calling it out to Julia and using it as the code gen. Kind of having little extern Julia, with Julia, and then Julia expression, and have that work inside your Python. So I would just say, think hard about using tools that create extension modules by hand that you edit yourself.
Yeah, and I would also add to that, if you do write something in C, which is a great language, by the way, you should make it Fortran callable. Make all the arguments just be doubles and pointer to double and integers, because then it's usable from anywhere. Then anybody in the world can call it from any language. So there's value to that.
That's a really good point. The C API is nice, except it doesn't play well with structures. That's not standardized. So
yeah. Well, structure layout is standardized, but it's from some it can be more difficult to access.
Yeah. That's different standards.
Yeah.
Next question. Yeah.
I think I'm going a little farther afield on the philosophy. I think when we started this discussion, we seem to be defining performance in terms of CPU cycles. And it seems that the migration is to, the migration is more in terms of increased parallelism into multiple cores, into GPUs, and into distributed systems. And I would also say that the trend, certainly in the last 10 years, is that the bulk of parallel systems are now Hadoop clouds and not compute clusters. I have not seen much movement in the Python community in terms of what I would think Python would be capable in a Hadoop environment. The NumPy sort of array structures in terms of modeling a variable as a data set could be extended to just consider data sets in a cloud, including string data. Does anyone have any thoughts on how we get to that point?
I actually have a lot of thoughts on that, but this isn't exactly the panel for that. I'm giving a lightning talk tomorrow that will discuss some things that we're doing in that direction specifically.
Okay, thank you.
Any other comments?
Parallelism is very exciting for many reasons. I mean, actually, one of them is that the little costs and latencies involved are very different. So I think there's more opportunity for dynamic languages and high-level languages because people really want to program in a very different way because it's not about getting something in a nanosecond anymore. So that's an exciting thing to me.
And nothing to add other than just that.
One of the important points, and I do have a lot to say on this topic. I just didn't want to hijack this panel. Yeah. You certainly want to be moving code to data more than data to code, which is most people move data around. That's kind of the modern paradigm with the stacks that are available. So you do have to kind of invert some things. And yes, parallelism is a big deal. I think Hadoop is more of a big deal is made of it than it deserves, but it is a very nice tool for doing things scalable. It's where we are now, and we can go beyond that. And in the Python world space, and I'll bring Julia into that space here. Python LLVM space, you can really do a lot more. So I'm excited about that.
Yeah, maybe we should move the discussion to the next talk, which is on Disco down in 106. So that's the next question.
Yeah, so this is basically a question for Travis and Jeff, specifically regarding LLVM from someone who's not terribly up on the details of LLVM. So Travis mentioned something that rings very true to me in that the reason Fortran compilers can emit this ridiculously fast code is that they have a lot of that high-level information baked into the language about array-oriented operations. And if you go from that high level down to 4 loops in C, and then to the compiler, you're losing a lot of abstraction. To what extent is LLVM the right tool for that job now and going forward? I mean, is it flexible enough such that sort of metadata, that sort of abstraction can be baked in at the IR level, or?
Well, so the LL does stand for low level.
Right.
So the LLVM itself doesn't do well. It's actually increasingly doing more advanced optimizations, but it's really just a cross-platform assembly language. It's a very, very good compiler building tool chain. There've been many portable assembly language kinds of things. C has been used as a portable assembly language many times, but LLVM is just sort of the really good one. It's just the one that people seems to have really nailed it, and people really like. And it's good to have, like Travis was talking about in his talk earlier, about that meeting ground between language developers and hardware developers. The hardware developers can go in and make sure their architecture is well supported, and then language developers target it, and so it becomes this meeting ground. And I don't know if it's perfect for everything, but you sort of have to agree on something at some point. So it's like, all right, we'll just agree to use this, and then see where we can take it. And people have done things like analyzing LLVM code to try to recover the loop structure. I mean, it's kind of a silly thing to do, that you start with loops and then you flatten it out, and then you have to run another tool to figure out where the loops were. But it's you do what you have to do. And so people have done things like that. There's a project to do polyhedral loop transformations against LLVM code by doing that kind of thing. Actually, in the new version of LLVM, they added some auto vectorization. So it actually is getting some pretty advanced optimizations, but you just have to know how to generate your LLVM code so that these things will kick in.
Yeah, LLVM doesn't buy. It really is just a common meeting ground. There's a lot of work to do from the compilers. Julie would have to do work. Dumbo has to do work in order to get the vision that we're looking for. But it's just a place to do machine code generation.
Yeah, and I guess it's flexible enough that the compiler can kind of inform its LLVM code generation with the high-level semantics
that's what the compiler would do, is inform the code gen, the IR generation. You
Gotcha.
write different IR depending on what you had written on the high level.
Yeah.
All right, next question.
So David stole most of my question, but so a slight variant. So we're seeing a lot of variety in low-level architecture these days. I can imagine that variety increasing in the next decade or so. Again, the answer might just be what you just said. But how robust are each of your projects to fairly radical changes in low-level architecture?
Well, I mean, from again, the LLVM thing, it's likely to be ported to whatever architecture is out there. So. So that's probably okay. In terms of radical changes, I mean, if the changes are too radical, we're all kind of hosed, right? But I guess we have to rely on certain things, staying a certain way. Basically that you have processors that have some kind of local memory, and there are other processors that have their local memory, and there's some kind of communication cost. And I assume that kind of situation, I would, for the foreseeable future, I think will hold.
Yeah, you're dependent on the LLVM. I like our bets, I guess. You're already seeing people when they come out with hardware having to put an LLVM backend, and then more and more large hardware vendors doing that. NVIDIA came out with their and retooled their whole stack to emit LLVM in the middle. They have another low-level representation called PTX and NVPTX, a new version. So it's just a meeting ground. Nothing's immune to, I hope somebody comes out with something, I don't know, the bio informatic chip or the quantum computing miracle. But if you have a type system and machine instructions, LLVM is going to do the job.
I think this panel is just being way too friendly. Let me throw a much unfriendlier question at you guys. So, sort of to throw open the talk, Andy started with stencil computing, right? Or he started with the 5-point Laplacian stencil in 2D, and that's a benchmark. But we can go pretty far with this idea of stencil computing, and there are a lot of things that fit into this general framework of working on structured grids, and there's data that's being computed, and it's got local impact, and local in, local out. So there's cache friendliness, there's other things to optimize that I'm going to say Python isn't the right language for. And that's my challenge, is there are specialized domain-specific languages that are being written to handle these specific problems, like stencil computations and these other things. There's special purpose languages being written for finite elements. So why do you think you're the language, or why do you think your approach is something that I want? And just to throw some examples of these challenge codes, right? There's Mint, which is this auto stencil tuning language. There's Poquar, which is also out of MIT.
Yeah,
and there's a similar PATIS project in Europe. So why should I consider investing resources into Python and trying to make a general purpose solution to performance when the special purpose solution can handle all of these other problems that the compiler, as I think you're admitting right now, can't handle or doesn't want to handle?
In part, I see the future as being kind of all of the above. You can generate a kernel with something like Pochoir and then call it from Python or wherever. So that that's pretty obvious, but that's part of the answer. And another part of the answer is that I agree with you. I mean, that Python itself, by itself, was certainly not designed to be as I called it, like an interface to performance programming. I mean, it certainly wasn't designed for that. And then NumPy and Cython and all these things have kind of tried to build it up to that point. But I think that what you get is you get kind of an accretion of type systems, and at some point you just have to say, okay, we just need a really good, strong, powerful type system, and then you can do kind of type-based metaprogramming to hook into the compiler in various ways and do custom code transformations and that kind of thing.
When you have a stencil compiler that can beat in Julia that can beat these other solutions, come back to me with that.
Well, I don't know if we can beat them, but I mean, a stencil compiler that generates C++ code, we could use the same ideas to generate Julia code, and it could perform comparably. If it's about using cache better, the right loop structure would perform better in Julia too. So I think we could do that. I can't say it would beat their performance, but
I would say the same thing. I don't think the goal is to beat performance of any particular domain-specific language. I mean, the goal, I think, is to integrate, to make it easy for people to use those domain-specific languages in a larger project. Right? That's the goal, is how do you provide an ecosystem that allows these things to communicate well? Instead of, okay, so now to use your stencil programming system, how do I use it? What do I do? If you generate an ABI that can be called, or if you generate, that's the question I would reflect back, is how does somebody use that domain-specific language in their larger infrastructure? And this is the sort of projects like LLVM certainly can help that interface, because you're now talking about the low level, and projects like a Python or a dynamic language on top helps at the high level with the coordination. And Julia is an interesting space. I really like some of the things they're doing. There's things that Julia is doing that I wish Python had. The way they're able to kind of manipulate. Call by AST is something I really like, and Julia kind of has something similar or close to that. So. Yeah, you want to kind of find the right balance between how powerful your dispatch system can be, and yet what can the compiler reason about. Yeah, that's right.
Yeah, I think along with that, so Python from the start was remarkably easy before Cython or anything like that existed. It was remarkably easy to pull in C code and create a C extension module compared to other languages like, I don't even know what it would be like in Perl or something like that. But
it's awful.
Yeah, thanks. And then Cython comes along and made that barrier even easier to work with. So it's just a very pragmatic language for pulling in all kinds of crazy things and giving this consistent language to call out to those other pieces. So.
Okay, maybe we have time for one more question and then we'll move to rants.
So this question is, I'm one of the other developers of Julia, so that's where I'm coming from here. This question is for the two Python guys here. There's this quote that I'm fond of by Henry Baker, which he was talking about Common Lisp, and he says the polymorphic type complexity of the Common Lisp library functions is mostly gratuitous, and both the efficiency of compiled code and the efficiency of the programmer could be increased by rationalizing this complexity. And my gut intuition is that most dynamic languages have the same problem, Python. Possibly. And so my question is, to what extent is that an issue? And you both are working in situations where you want to generate nicely typed, fast, compiled code, and so you probably have some insight into to what extent that's an issue for Python specifically.
So could you rephrase the question a bit?
Yeah. So the quote
first part you said.
The quote is the polymorphic type complexity of the Common Lisp library is mostly gratuitous, and both the efficiency of compiled code and the efficiency of the programmer could be increased by rationalizing it. So I think the point he's getting at is that you have functions where, depending on the value of an input, you might get a float, you might get a string, you might get an integer.
Yeah.
And that's fine in a dynamic language, but then when you're trying to generate efficient compiled code, it's a problem. So I don't know enough about Python to know to what extent that's an issue and to what extent it's not an issue.
Yeah, well, I mean, Pyrex was the originator of, it was the previous project that Python forked and built on top of. And it was, its whole reason for being was just, all right, I have Python, I want to inject types in here and be able to get the information to the compiler to give me fast stuff. And Python took that and just ran with it and said, okay, how can we cover all of Python in this language? How can we, optimize the generated C code to within an inch of its life, and all those features? How can we add in parallel support and tap into OpenMP from within Python syntax, things like that. So it's very pragmatic language that's just really motivation is just to bring in types into Python in a not horrible way. It does absolutely depend on the programmer knowing details of C, knowing details of the lower level language that you're compiling out to, whether C or C++, to be able to leverage all of that performance and be able to make that work as well as possible. So it's something that like working with C++ in particular can be a challenge in Python, because if you're wrapping a templated class, it can be you have to turn to some other templating tool external to Python to get it to handle all the specific types that you want to instantiate from your C++ templated class. And so a number of ways in which it can be done better, but Python's always taken a very pragmatic approach to say, okay, how can we get something in people's hands now that'll be useful and allow programmers to at least access typing information and add it to Python. So I don't know if that addressed much of your question at all, but it's at least a bit of the background of why Python and Pyrex and Python existed in the first place, and just the fact that they've always emphasized pragmatism, getting stuff in people's hands so they can at least get these languages talking to each other now for existing projects.
So that's probably all the time we have for questions. If you guys want to give a 1-minute wrap up and start with Travis.
Well, instead of ranting, I mean, your question's a good one. I think he's ignoring users a little bit too much and thinking too much about programmers. One reason Python's been successful is because people get started quickly. And non-rationalization allows that, really, rather than saying, oh, you got to specify all this stuff first. Now, at the same time, NumPy really kind of provides a gradual slope to rationalization because you're typing everything. But it could be improved, and in fact, should be. I mean, there's some definite things I've learned along the way. I mean, I did it as a scientist who was just trying to get stuff done without ever having, I couldn't even understood that quote, I think, 5 years ago. But now that you see kind of the point, NumPy does kind of make that gradual transition to a type system, and I definitely agree with what Jeff said, is that we really should just have a typing mechanism. That's a key feature of NumPy really is the dtype, and it needs to be improved. Kind of what's there is I don't say it's half-baked, but maybe 75% baked, and it could be definitely improved.
Jeff, your last minute.
All right, well, I guess my rant would be, won't somebody please think of the expressiveness? And what I mean by that is the declarative information can be very rich and helpful, and we should embrace it more. And you know, once you start adding declarations to things, if you add a declaration, you don't want it to suddenly make your code monomorphic. Like you said, something's a double, but now your code can only handle doubles. So you eventually need something like type variables. You know, so it's really, to me, it's really more about the expressiveness of being able to define new abstractions and user-defined types and have it work efficiently at the bottom level.
And Kurt.
So my rant is about the denigration of Fortran that goes on in modern scientific computing. I love Fortran. I think it's a fantastic language, especially if you only focus on modern Fortran 90, 95, 2003's array expressions and array capabilities.
I'm going to actually agree with you here.
Okay.
Big second.
Yeah, me too. I'm not claiming the panelists are, but in general, you know, like, first of all, spelling Fortran with all caps, that's what you did in Fortran 77, but since then, it's capital F, lowercase everything else, so
that's a major technology improvement.
And I'll get you some Fortran lovers, some tar and feathers in just a minute. So thank you very much for coming to our panel and participating. I think